Hi, today I am going to discuss about speed control of three-phase induction motor. As we know that the speed of the motor N is equals to 1 minus S into Ns, where S is the slip and Ns is equals to synchronous speed. So from this equation we can say that the speed of the motor is depends on the slip and synchronous speed. So based on this formula, the speed control of induction motor can be done using two techniques. One is slip control technique and second one is synchronous speed control technique. So slip can be controlled using voltage control method, rotor resistance control method, rotor EMF injection method, while the synchronous speed control technique can be implemented using pole changing method, voltage frequency control method and cascading of induction motor, and these two technique can be used for slip ring induction motor. Slip ring induction motor. Voltage control method. Assumptions: load torque is constant. Under stable operating condition, the load torque is equals to electromagnetic torque, and electromagnetic torque is 3 by omega s V1 square R2 dash. Here we can see that the R2 dash is also constant, omega s is constant and 3 is also constant. So from here we can write down the equation like this: s V1 square is equals to constant, or we can say that s is proportional to the 1 upon V1 square. If this is the approximation circuit of a machine, then this is the applied voltage V1 and this is Jx2 dash and this is R2 dash divided by S. Okay, so from here we can write down the current equation: I is equals to V1 divided by R2 dash by S, because x1 is very small. Okay, so it will be as V1 divided by R2 dash, and this is the current equation, we get it here. Okay, so from this equation we can say that I is directly proportional to the slip. If the slip will increase, it means current will also increase, and from this equation we can see that the slip is proportional to 1 upon V1 square. It means if the voltage will decrease, so slip will increase. And why we are decreasing the voltage only? Because if we apply the higher voltage from the rated voltage of the motor, their winding may be burned because of the insulation failure. Okay, therefore in this technique we will apply only the voltage across the motor terminal below than their rated voltage. Okay, so if we are decreasing the voltage, the slip will increase. So from equation number 2 we conclude that the voltage will decrease and slip will increase, and if the slip will increase, we know the formula for the speed of the motor, that is 1 minus S into Ns. If we are increasing the slip, it means the rotor or the motor speed will decrease. Now from equation number 3 we can say if the slip will increase, the current will also increase, and if the current will increase, we know that current is responsible for the I square R losses. If the current will increase, it means this losses will increase, and because of this losses, heat will increase. Now if we talk about the power factor of the motor, so that is R2 dash by S divided by R2 dash by S whole square plus X2 square, and this is the R2 dash by S dominant If the slip is increasing, so R2 dash by S will decrease. So if R2 dash by S will decrease, it means power factor will decrease. We can see the torque versus speed characteristics for this method. The starting torque TST or tau st is proportional to the E2 square, and E2 is proportional to V1 square. It means if we are increasing the if we are decreasing the voltage V1, it means the starting torque will also decrease. As we can see, the V1 is the rated voltage, so the starting torque is high. As we are decreasing the applied voltage, the starting torque is also decreasing, and their speed is also decreasing. We can see here, for example, we have considered the fan load, so the speed is also decreasing due to increment in the slip. Rotor resistance control method. This method is useful for slip ring induction motor, because in the slip ring induction motor we can add the additional resistance in the rotor circuit. Assume load torque and supply voltage is constant. So under stable operating conditions, we know that load torque is equals to electromagnetic torque Te, and that is equals to 3 by omega s as V1 square divided by R2 dash is equals to constant. Okay, so if here we have considered that the V is constant, omega is also constant, and 3 is also constant, it means we get that S by R2 dash is equals to constant. So from this formula we can say that the slip is directly proportional to the rotor resistance, and if we are adding the more resistance with the rotor resistance, it means we are increasing the value of the rotor resistance, it means the slip will also increase. We know the formula for speed is equals to 1 minus s into ns, and if the slip is increased, it means speed of the motor will decrease. Okay, in low slip region the torque is proportional to the slip. Okay, so if the resistance will increase, slip is also increased with respect to the rotor resistance, it means speed will decrease. This is the one conclusion. Higher copper losses will be there. Why the higher copper losses? Because we are adding the resistance, and resistance are responsible for the I square R losses. So if the I square R losses is higher, and that is called copper losses, it means low efficiency. Speed control can be done below the base speed of the motor. Why? Because we are adding the resistance, and by adding the resistance we are going to increase the slip, and if the slip will increase, so we will get the speed lower than the rated speed. Now let me talk about the starting torque. So we know the formula for the starting torque is equals to K E2 square R2 divided by R2 square plus SX2 whole square. Okay, so from here we can see that the starting torque is directly proportional to the rotor resistance. It means if we are adding the more resistance, the starting torque will be high, as we can see here for the different values of R1, R2 and R3, the starting torque is shown here. Okay, rotor EMF injection method. This method is useful for slip ring induction motor, because in the slip ring induction motor we have the open terminal of the slip rings. So using the slip ring terminals we can inject the additional EMF from the external source. Assume load torque and rotor resistance is constant. The frequency of the injected EMF is same as the rotor current frequency. Under stable operating conditions, electromagnetic torque Te is equals to load torque is equals to constant. We have assumed it is equals to SE2 square divided by R2 dash. So from here we can say SE2 square is equals to constant, or we can say that the slip is proportional to 1 upon E2 square, and if we are increasing the value of E, slip will decrease. We know the formula for the speed of the motor, n is equals to 1 minus s into ns, and if the slip will decrease in this formula, it means the speed of the motor will increase. Let me consider case number 1. The injected EMF is in phase of the rotor EMF. It means rotor EMF is E2 sin omega t, and if E in sin omega t is the injected EMF, so both are in phase, so the resultant will be ER is equals to E2 sin omega t plus E in sin omega t. Okay, as shown here, this is E in and this is E2. Okay, so resultant will be E2 plus E in sin omega t. As the resultant rotor EMF ER is greater than the rotor induced EMF E2, so the slip will decrease to maintain the torque constant, and if the slip will decrease, it means the rotor speed will be increase. Okay, if S is negative, then N is greater than Ns. So motor run at higher speed as compared to the rated speed of the motor. So this is the most important advantage, that using the rotor EMF injection method we can achieve the higher speed of the motor as compared to the rated speed of the motor. Now let me consider case number 2. The injected EMF and rotor induced EMF are out of phase. We can see in this picture, this is the induced EMF and this is the injected EMF. Okay, so ER is equals to E2 sin omega t minus E in sin omega t. Okay, so the resultant will be ER is equals to E2 minus E in sin omega t. So the resultant rotor EMF will be less than the rotor EMF or induced EMF in the rotor. As the resultant EMF ER is less than the rotor induced EMF E2, so the slip will increase to maintain the torque constant. Okay, and if the slip will increase, it means the motor speed will decrease. If S is positive, then N is less than Ns. We can see here. Okay, so the motor run at the lower speed as compared to the rated speed of the motor. So this is the another thing we found out, that using rotor EMF injection method we can run the motor at the rated below as well as higher speed as compared to the rated speed. We can achieve the higher speed as well as lower speed. Thank you.